the risk from collisions is already causing satellite operators to have to perform maneuvers to dodge exotic methods as well, using lasers. It's already a sign that the Kessler Syndrome has kind of started. We've already seen closures of airspaces in Europe, and we're going to see more of that. How did we let that happen?
Will we put so much stuff into space that we end up trapped here on Earth? I mean, it sounds quite far-fetched. As we know, space is enormous. The universe is vastly larger than any human could possibly comprehend. And so it seems, I guess, unimaginable that we could accidentally trap ourselves on the planet. But is it a possibility? Because although the universe is absolutely enormous, there is a limited amount of space around Earth. And we already put lots of stuff up there, and big companies like SpaceX and Amazon have plans to put even more stuff, tens of thousands of satellites, into orbit around Earth. Some people believe this could cause a phenomenon called Kessler Syndrome, which sounds like something out of Star Wars, but may very well happen. So to explain what it is, whether it's likely to happen, what happens if it does happen, and if there's anything we can actually do about it, I'm joined by Professor Hugh Lewis, a professor of astronautics at the University of Birmingham. So if you wouldn't mind, please, introducing yourself and some of the work that you do, and then we can talk about space.
Hello, so I'm Hugh Lewis. I'm a professor of astronautics at the University of Birmingham. So that means I study lots of things to do with space, but in particular, I really focus on space debris. Lots of people call that space junk, space trash. It's the rubbish that we leave behind in space. And a lot of the work we do is about trying to predict the future.
I mean, I think people have a general idea that we put satellites into space for GPS, satellite internet, but I think most people probably struggle to conceive how much stuff is up there, all of the sort of systems that depend on it. So could you give us a quite difficult question, but could you give us sort of a brief overview of what is up above us circling Earth?
Sure. I think most people are probably familiar with using a navigation system, sat-nav, for example, in the car or on the phone, and that's a service that is provided by satellites. So as I say, that's probably the most familiar, but those systems also provide us with timing data, which is really important for things like banking. So when you do your banking, you're probably using satellite services as well. We're also probably really familiar with weather forecasts, and weather forecasting has really seen a huge improvement over the last few decades thanks to satellites. And it might seem, perhaps irrelevant to most people, but, in places where, flooding happens, where big storms happen, those weather forecasts, make a huge difference. We also use satellites to understand the planet. A lot of our understanding around the climate, that comes from having satellites in space. So a lot of the satellites that we see in orbit really represent vital services to us, almost like infrastructure, like the electricity supply, like water supply. We probably couldn't operate as a modern society without those satellites. So they are really, really important. And therefore, that means that they're really vulnerable to threats from space debris.
And so are there rules and regulations around what people can put into space? I mean, I know there is a sort of technical blocker of not everyone has the physical or financial capacity to put stuff in space, but if I started a space company tomorrow, could I just put something in space, or are there sort of checks before I do that?
Yeah, there are lots of checks actually before you can fly and operate a satellite. So here in the UK, you'd have to apply for a license to operate a satellite. So your application would get scrutinised by the Civil Aviation Authority. They're the regulator. They decide really whether your plans can go forwards, and they look at various things to do with your plans, including what you're going to do about minimising the creation of space debris. And all that traces back to a treaty that the UK signed a long time ago called the Outer Space Treaty. So that was something that was organised by the United Nations. And that treaty basically says that we can't interfere with other people in space. We shouldn't contaminate the orbital environment in any way. And that sets out lots of responsibilities that the UK government has. So what they do is they make sure that every company who wants to fly a satellite just kind of sticks to those rules that the UK government has kind of signed up to. So it involves costs. It involves looking at a set of kind of guidelines in terms of how you need to operate, and demonstrating that you're going to follow those.
And just to get clarity on the term space debris, is space debris always the result of something man-made, like chunks of satellite, or does it also include tiny space rocks?
Yeah, it can include both. And I think actually you're right that it's perhaps a bit of a confusing term. So when in our research, when we talk about space debris, we refer to the artificial space debris. So that's everything that humans make, satellites and parts of satellites and rockets and so on. But you're right, there is a population of natural debris. These are the micrometeoroids that kind of whiz through Earth orbit, thanks to comets and so on that are in orbit around the sun. Those tend to be, very, very small particles, but travelling extremely quickly. But the biggest distinction is the fact that the artificial space debris is in orbit around Earth, and the natural space debris is in orbit around the sun.
Right, okay. So what is Kessler Syndrome? Can you talk about, I guess, how the theory came about and then what it actually means?
Yeah, so nearly 50 years ago, two researchers, Don Kessler and Burton Corpellé, published a paper. So it was in 1978. And that paper was describing the formation, essentially, of an artificial ring around Earth, made up of the artificial space debris. So it was a warning, if you like, way back in the past about what could happen in the future if we didn't start to manage the situation in orbit. And it was really quite stark, saying that before the beginning of this current century, before the year 2000, that we could be in trouble unless we started to take some action. And it described a process by which collisions occur between the objects in orbit. So basically they're whizzing around at extremely high speeds. So the speeds are around 7.5 kilometers per second. But the relative speed, so that's as the two objects move towards each other, could be up to 10 to 15 kilometers per second. Just to put that into perspective, it's like going from London to New York in about 11 minutes. It's extremely fast, really, really highly energetic. So if objects collide, they produce huge amounts of fragments, which then go off and have the potential to hit other things as well. So Don Kessler's and Bert Corpellé's paper described that collisional process and warned about the potential for those collisions just to keep going on, a cascade, as they called it. And that process became known as the Kessler Syndrome. It was actually called that by one of Don Kessler's colleagues at NASA, just almost as a joke, but the name stuck. And nowadays it's synonymous with talk about space debris, and it actually was the idea behind the movie Gravity. That movie was all about essentially a vision of the Kessler Syndrome. So that cascading process is the thing that we really worry about, because it starts to cause major issues for all those satellite services that I was talking about.
So is there any way we can track tiny space debris? Because you hear all the time that astronomers often struggle to even track relatively large asteroids, maybe if they're coming from the direction of the sun. So I imagine it'd be very difficult to track tiny chunks of space metal or space rock.
Yeah, I mean, tracking space debris is a real challenge. We have the advantage of using radar on Earth to look at orbits that are relatively close to Earth. So probably up to about an altitude of 2,000 kilometers. We can use radar quite effectively to spot objects and to track objects that are probably about the size of a tennis ball. So that really helps. As we go further out into Earth orbits, so higher up, essentially we can't use the radar anymore because they don't have the power So we use optical telescopes, for example. Again, many of them Earth-based, but they're not as sensitive. So when we get out to, tens of thousands of kilometers altitude, you're seeing things that are probably the size of a fridge door, or microwave kind of door size. So much bigger. And the problem really is with the things that are smaller than that tennis ball, smaller than that fridge door, because we can't track those objects. So we can't provide warnings to the satellite operators to say, hey, in a couple of days' time, you're going to have a close approach with this object. It has to be bigger than that tennis ball in order for us to provide those warnings. Yet, because of the speeds with which these objects travel, they can still at least disable a satellite and probably cause quite a lot of damage. So things that are the size of a thumbnail, those can destroy a satellite, almost certainly disable it. So we're aware of that risk. But the only thing that we can really do for those types of objects is to put shielding on the spacecraft, on the satellites. But shielding is really expensive. It's a huge amount of mass. So there's really only a few satellites in orbit that have shielding on, and that's those are the crewed spacecraft, like the International Space Station, the Chinese space station. They have shielding on, and that shielding is effective for objects that are smaller than your thumbnail. Anything bigger than that, and they have to try and dodge out of the way.
That sounds very terrifying. So is the primary problem with Kessler Syndrome that it would interfere with our ability to have other things orbiting in space? Or is it that it would interfere with our ability to launch, beyond Earth's orbit, explore the moon or Mars? So is it the fact that it's interfering with us leaving the planet, or is it interfering with stuff that we want to put in orbit, effectively?
Yeah, so Kessler Syndrome is, there's kind of a spectrum of possibilities, really, and outcomes that emerge. So all of the things that you're talking about could potentially happen. The risk from collisions, not just cascading collisions, but just any collision, is already causing satellite operators to have to perform maneuvers, to dodge, to avoid the debris that's already there. That has that's important for companies operating these satellites, because they're losing time in the correct orbit. They're not necessarily able to provide the services that they want to be providing. And the more debris there is, the more that happens. So there already is a cost associated with the collision risk. We do our best to try and reduce that by manoeuvring, but that still exists. And as more objects get put into orbit, as those objects fragment and break up, potentially due to collisions, more manoeuvres have to be performed. The other thing that happens is that the gaps that we have in a launch window. So when a rocket launches, typically you want to put it into a specific orbit, whether it's going to the moon, Mars, or whether it's going into Earth orbit. There's normally a very precise orbit that you're trying to put it into, and that requires a specific timing for the launch. But if you've got debris flying overhead, you can't launch, because that presents a collision risk, and you particularly don't want to do that if you're carrying human beings on the rocket. So that those put breaks into your launch window. So the more stuff is up there, the more of those breaks you have in the launch window, and it gets harder and harder to find the right kind of gap. And if you're trying to launch to a planet out into the solar system, your launch window could be just seconds long, in order to achieve the right orbit. So what do you do if that window is closed because you've got debris going over it? And that's already we're starting to see that already. So the Kessler Syndrome just describes that situation, but even worse, where we're unable to launch safely, or where we have to accept a particularly high level of risk in order to conduct the kind of space activity that we want to. So that is already happening. And it's an argument that we have for obviously trying to stop things getting any worse. But in many ways, it's already a sign that the Kessler Syndrome has kind of started, that we're already starting to see that kind of effect. We haven't had many collisions, perhaps in orbit, but the process isn't this instantaneous thing that happens. It's not like nuclear fission, which is another cascading process which kind of happens very, very quickly. This is something that happens over generations, yet we're already starting to see some of the effects.
So it might almost be that the point of no return is crossed before we even realise it. I guess because of the nature of it's sort of a chain reaction, and one piece might break into 3 pieces, might break into 9 pieces, might break into so on, so on, so on, that we might not even realise until it's too late.
Yeah, I think you're right in the sense that it could be happening under our noses, as it were, and we're perhaps not necessarily aware. And I think in part it's because it's a slow process. And it's also perhaps a misconception that you need to have a huge number of objects for this process to happen. One of the things that Don Kessler described was the what is known as a critical number of objects, the number of objects that you need in order to kind of trigger this process. And he did a lot of work on this. And that number changes the further away from Earth you get. And it changes because the atmosphere is our friend in terms of space debris. The atmosphere provides this wonderful mechanism for removing a lot of the space debris. It changes the orbits. It's such that those orbits shrink and eventually the objects burn up. But the higher up you go, the less effective the atmosphere is. And hence the lower the critical number of objects. So you get to altitudes, and it's not very far away from Earth. You're talking about altitudes probably 1,200 kilometers, 1,400 kilometers above Earth, where the atmosphere is so sparse, so thin, it's not doing anything to remove debris. And you just need a handful of objects there in order to reach that critical number that Don Kessler described. So it's not thousands and thousands of objects at all. And I think that becomes, that's the misconception that people have, that it's just a few objects. And we've already exceeded that number of objects in several orbits. So according to Don Kessler, if we continue to use those orbits, we will see that Kessler syndrome in action. And I think that's why we, people in my field often say that the Kessler syndrome has already started, even though it's this, it seems as though it's not apparent. It is happening under our noses. And it's a process that will go on now without our intervention for many years. But in order to get the true kind of Kessler syndrome, we have to do something that I think I'm hoping that humanity wouldn't do, which is to ignore the problem and just to keep doing what we're doing, which is to keep launching lots of objects, to perpetuate the problem.
So I suppose the point isn't, as you say, that you need a lot of objects for this to happen, but I suppose the more objects we have in space, you increase the likelihood of that happening to one of those objects. So, I mean, are we being exposed to forward with these massive satellite constellations? I mean, I'm sure you've seen it. It's becoming increasingly common to have these sort of space internet services. I mean, Starlink is very widely available now. Is that a big risk factor? Because I suppose it's hard for the public, I guess, to get a sense of how regulated that is. I mean, like you say, they apply to put these satellites into space, and debris is part of that application process. But I mean, I often feel like technology is very difficult to regulate. Would you say that also applies to space technology? Because ultimately all these companies and countries will want to be primary operators in space, and America will want to have better space service than China and better than Russia, and so it worries me that might drive us to put more stuff in space irrespective of Kessler syndrome. So I mean, are you optimistic?
I think I have to remain optimistic, otherwise I may as well kind of give up now in terms of the research. But I think you're also right to a certain extent, that we are, I say we, humanity, is making much more use of space. And a lot of it is commercially driven. So there are companies now who are providing services that consumers pay for. And so you mentioned Starlink, and Starlink has millions of customers around the world, providing internet services from space. And that's a great thing, right? The fact that we have these opportunities that are provided from space to offer services that we couldn't perhaps get in other ways. So it's a fantastic opportunity, and those companies, such as SpaceX, Amazon, OneWeb, that they understand the problems. They understand space debris is going to harm their business. So what they do is they look at the regulations that they have to follow, and they often go further than those regulations. So that's actually a really, really positive thing. The regulations kind of describe the minimum that the companies have to do, but those companies go much further than perhaps they need to with respect to the regulations. And that's important, right? Because they are operating tens of thousands of satellites. And the thing that Don Kessler and Bert Corpelle said that would drive the Kessler Syndrome is essentially increase the number of objects and increase the size of those objects. And those two things, those increase the collision rate that we might expect. So SpaceX maneuver. Their satellites perform huge number of maneuvers every year to try and avoid the collisions that they would otherwise probably experience. So just in 2025 alone, the Starlink satellites performed about 300,000 maneuvers to try and avoid colliding with other objects in orbit. So that's a huge thing that they're doing. That costs them, costs SpaceX in terms of their bottom line in order to try and maintain the safety. So whilst I think it's fair to say, regulation could be better around the world, the fact is that these companies are very much aware of their responsibilities in orbit and are doing a great job in trying to go beyond them. The question that we ask of researchers is that still sufficient? And that's an open question, right? So whilst the companies are doing really, really good work to keep safe, to ensure that other people can operate around them, there's a question which is, could there still be problems arising as a result of their operations in orbit? And then if so, what is the next step? What else do they need to be doing? And that's the thing that I think we need to address, not just for the current crop of satellites, but for what's coming next. We've seen proposals for a huge number of satellites, and we need to try and help those operators to maintain their safety and also the sustainability of operations into the future. So I remain optimistic because these companies are aware and because they're actually going beyond what they're asked to do by regulators.
The manoeuvring I find so interesting because, you think of satellites as just sort of circling Earth in a very sort of graceful way, but the idea that they're almost like dancing around, constantly shuffling out of the way. How does that physically work? Is it that they learn about the debris because of sensors on board, or is it something that's passed to them from Earth? And then how does the actual manoeuvring work? Do they have sort of like mini thrusters on board?
Yeah, that's exactly right. So the satellites have propulsion systems, thrusters that enable them to change their orbits, and to change their orbits in a reasonable amount of time. So the satellites essentially receive data. Normally, the data is collected from the radar systems that I was talking about earlier, and potentially the telescopes. And the data essentially represents the orbits of all the objects that we're currently tracking. And what we can do with that information is we can use essentially computer models to predict the trajectories into the future, and then we can look to see whether any of those trajectories intersect. So essentially, there's potential for a collision, and that's the data that the satellites kind of see. and then they can make a decision about whether or not to maneuver to avoid that close approach, to avoid that collision. Starlink and SpaceX, they've gone even further than that. They're using data that they're collecting on board the satellites. So all those satellites, and there are about 10,000 satellites in the Starlink system that are operational. Each one of those has a tracker on it. It looks at the stars to figure out its kind of attitude in space, its orientation. But they're also seeing all the objects that are kind of passing through that sensor. It's basically a camera. And with 10,000 satellites in orbit, they collect a huge amount of data about all the objects in orbit. So they also supplement the information that they receive with their own kind of data. So they're able to detect objects and then predict the trajectories even hours in advance, and make maneuvers to avoid any potential collisions. It's a really remarkable system, and it's been shown to be effective, in terms of preventing any collisions. We haven't seen a collision in the Starlink system, since they've been operating. So that's kind of good news. I hope that continues.
So before we get on to the idea of maybe what we can do after the fact in terms of removing debris, are there any other ways of, any other prevention methods? I mean, I know we've talked about shielding, some of the maneuvering, having regulations. I mean, what else could we be doing to limit this from happening in the future?
Yeah, I think it's important to understand that the shielding and maneuvering don't reduce the debris problem. It's really an adaptation to the environment, which is full of debris, right? So what we're really after are ways to prevent the creation of new debris, and potentially to remove the existing debris that's in orbit, to reduce the problem down, so we can minimize how many maneuvers we need to make. We can operate satellites potentially without shielding. So that's the difference, I think, between the adaptation. And that's something that satellites have to do now to operate in the environment, and then this mitigation that we talk about, and that's the prevention of new debris, and then remediation, which is about removing the debris, and we want to do all of those things. So we have to do the adaptation. The mitigation certainly helps, but those two things alone are not sufficient. We also have to remove the debris from Earth orbits, so that we can shrink that problem down. There are a lot of technologies that have been looked at to undertake the removal, for example. So we can go up with robotic arm, spacecraft with a robotic arm, grab a debris object and then drag it down to burn up in the atmosphere, or to move it somewhere into a graveyard orbit, that kind of thing. And that's a very kind of popular approach, because we really understand robotic arms and their use in space. I mean, there are robotic arms on the International Space Station that they're used almost on a daily basis. So that they're really, really well understood. But then you've got a lot of exotic methods as well for removing debris. People talk about using lasers. Lasers on the ground, for example, that essentially illuminate a debris object. And what they're doing there is they're heating the surface, and that heated surface essentially turns into a plasma and just ejects like a jet thruster, a rocket thruster. All that material just comes off and it pushes the object. So that kind of idea has been really well explored, because it seems like a very straightforward method, but it has limitations. And then we look at other types of objects, throw a big net over it or a bag to collect up the debris. I think, back when Elon Musk was talking about Starship, use Starship to grab a lot of objects. They've got a huge payload capacity on that rocket. So why not, send something into orbit, but then grab a whole bunch of stuff on the way back, to try and clean up the environment. So those are all technologies that have been proposed, but we haven't really got going with. we've been able to demonstrate some of the technologies, but we haven't got this sustained activity that would be needed. And then in the middle, that mitigation, that's something that the operators have to do now. So that means designing your systems so that they don't release debris. So that seems sensible, right? But up until a few decades ago, what would happen is that if you have a telescope on your satellite with a lens cover on it to cover it during the launch, you just let that lens cover float away. Other things would just float away from the spacecraft. Now you kind of want to keep them attached as far as possible. You put a tether on the lens cover for your telescope to make sure it doesn't float away. So all those things you build into the design. You limit the amount of time that your satellite spends in orbit after you've finished your mission. And you normally do that by moving to a graveyard orbit or lowering the orbit so that essentially the atmosphere helps you shrink the orbit down and burn up.
So is a graveyard orbit where satellites that you no longer need, they just stay in an orbit where it doesn't matter if they break up and they'll just continue circling Earth? Or is a graveyard orbit when it will also then deorbit into Earth? Or are they two separate things?
Yeah, they're two separate things. So we tend to use graveyard orbits when there's too much energy or too much propellant needed to bring the orbit close towards the Earth, so the atmosphere essentially burns it up. So the most commonly used graveyard orbit actually is above the geostationary ring. So that's the ring of satellites that is around Earth, around the equator. And we used to nowadays we use streaming, but just a few years ago, that's where you get your satellite TV from. It's an altitude of about 36,000 kilometers, so it's quite a long way from the Earth. No atmosphere there to speak of to drag things down and to burn them up. So we use a graveyard orbit. So when the satellite has finished its mission, it gets boosted up out of that geostationary ring, which is very heavily populated with communication satellites, big, expensive satellites. So you want to keep that orbit clean as far as you possibly can. That graveyard orbit is several hundred kilometers above the geostationary ring. And the satellites, they go there and they are left there. They're kind of switched off. They're passivated, so there's no energy stores left on board the spacecraft that would potentially lead to an explosion. And they're left there, and they will remain there for a very, very long time. Hundreds, thousands, potentially hundreds of thousands of years. They'll be up there in those orbits. We don't want them to break up. Still, so we do our best to minimise that from happening, but it's far better that they are there than left in that geostationary ring, because that would interfere with the operational satellites, and that's kind of the best that we can do at the moment. It's not really a great solution over the long term because we just keep throwing more and more things into those graveyard orbits. Now, as you come down closer to the Earth, we don't really have graveyard orbits in the same way. So navigation satellites, the ones that give us the GPS and so on, they have graveyard orbits. But when we get to low Earth orbit, we tend to want the objects to be removed from those orbits by lowering them into the atmosphere as far as we possibly can.
We've seen, certainly in recent years, these stories about an out-of-control Chinese rocket, for instance, falling back to Earth. And I assume the intention generally with this stuff that is deorbiting back to Earth is to have it land in the sea. But often when you sort of see those sort of traces of the possible landing zones, sometimes it is also over land. And so I suppose, is that a safe way of dealing with the debris, is to just sort of have it fall back to Earth and just sort of hope that it doesn't land on a house or a car or a person?
Yeah, there have been some really high-profile examples where some very, very large objects have re-entered the atmosphere in an uncontrolled way. So normally, when you have very large or very massive objects, which could potentially pose a risk to people and property on the ground, you want to actually perform a controlled re-entry where you target a particular location. The ocean is a really good example. The Pacific Ocean in particular, because it's so big, and there's just nobody around. So you want to companies and spacecraft operators to do that as far as possible, but that's actually technically is really hard, and also it involves a huge amount of fuel. So rocket stages, the parts of the rocket that deliver the satellite into orbit, are also orbital, but they carry lots of propellant, and they're able to use some of that propellant to change their trajectory, so they do re-enter and potentially end up in the ocean. But when you've got a satellite that's been operating for several years, and it's come to the end of its mission, and it was never designed to carry enough propellant, then those objects, those can re-enter in an uncontrolled way and can strike the land surface. Now, we've got two things in our favour. One is the atmosphere. So as the objects are travelling, I've already talked about the speeds with which they travel. When they hit the atmosphere and the denser parts of the atmosphere, they are heated, and they are heated to very, very high temperatures, and that tends to essentially destroy the satellites in the atmosphere, which is great, because then most of the material will never reach to the surface. And then the other thing that's working in our favour is that 70% of the Earth is covered by oceans, sea, where there are no people, no property around in general. So those two things tend to mean that the risks to humans are relatively low. So we have re-entries every single day of objects that are fairly big, but we never see them because they're coming in over uninhabited areas, quite often. And occasionally you see, clips on YouTube and so on of an object re-entering, but they're burning up high in the atmosphere. That's what you're seeing. What we have learned over the last few years, though, is that all those objects burning up in the atmosphere, that's not great for the atmosphere. They're potentially releasing chemicals that can influence the destruction of the ozone hole. Ozone holes are not good for human health at all. So we kind of want to prevent that from happening. We also use fly a lot. So all these objects that do survive the re-entry, they're passing through potentially busy airspaces. We've already seen closures of airspaces in Europe, for example, as a result of objects that re-enter. And we're going to see more of that, I think, in the future. So it's not, re-entering objects as a way to get rid of them from orbit is not necessarily the best thing to do, because we're kind of trading one environment and harm in that orbital environment with potential harm in another. So we really have to have a joined up approach to this to try and understand what the best approach might be.
You talked a little bit earlier about how we haven't got very far with the idea of netting debris or sort of blasting it with lasers. Is that because it's almost deemed by the science community not an immediate enough a threat, or is it just the case that it's hard to get funding for that kind of science? I mean, because you would think that it's a very interesting area. You would imagine there would be public interest in it, but I don't know. I mean, how do you feel like the funding is for that science?
Yeah, I think you're right that it's a difficult concept to realise. If you think about what you want to do with debris removal, right? Especially missions where you send another spacecraft up. So from a technical point of view, it's one of the hardest missions you could possibly envisage, because you're going up to potentially a really, really big object that is not in control. Okay, so it could be tumbling. It could have things sticking out from it. It could have, if it's a rocket stage, could have residual fuel on board. And your job with your spacecraft is to go up and potentially to grab it and to maneuver it somewhere, right? So that's really hard, really risky. Not only that, the reason you want to kind of go and get it is because it poses a risk. It could be hit by something. So you're going to an object which is dangerous, essentially, to your mission. and really hard to get hold of. So from a technical perspective, you want to make sure that you do that really well and effectively, without essentially elevating the risk in any way. So you need to practice that. You need to really get the technology right, and that's kind of what we're doing. So that kind of slows us down because it needs to be done in a robust way, without causing any more harm in the environment. That would be bad, right? If we send these missions up to remove debris, we just create more. So that slows us all down. But you talked about the funding, and that is the one of the other aspects. It's enormously expensive, right? You're sending another space mission into orbit. That's probably hundreds of millions of pounds, hundreds of millions of dollars, and there's no scientific return, right, on that mission. You're just going to grab some junk. You're basically a really expensive litter picker going into orbit to grab space debris. So whilst it's great from an environmental perspective, there's no other really scientific merit to that kind of mission. So who's going to pay for that, right? The only real way it starts to become incentivized is if you start to say you have to remove your spacecraft and rocket stages from orbit when you finish with them. If you can't do it yourself, you have to employ some other company to do it for you. And if that becomes part of kind of if government policy becomes regulation, then companies would seek other companies to help them remove the space debris at the end of the mission. And that's a way to incentivize it, is through the regulation, to mandate it. From a commercial perspective, there isn't really a market for it, unfortunately, and because it's so difficult, it's a really expensive endeavor. So unless you can figure out who's going to pay, then it is almost a non-starter.
So to wrap up, I guess if you were almost pitching for funding for solving Kessler Syndrome, what is the worst case scenario? If we don't get it right, the regulation isn't enough, what does it sort of mean for humanity? And then just as a follow-on, are you optimistic that won't happen? Do you have faith in humanity to solve it?
Yeah, I'll answer that question first, right? I think rather than thinking about, what if we get it wrong, think about what if we get it right. We probably, I grew up with, Star Trek and the shuttle missions and so on. So I was really optimistic about space anyway, growing up, and that science fiction future is something extraordinary to perhaps contemplate and to envisage. And wouldn't it be great if we could achieve that? Humanity on other planets, in a sustainable way, without creating junk everywhere we go. So that's how I tend to try and think about it, is what if we get it right? And then how do we make that happen? The flip side, what if we get it wrong, is really concerning, because, history has shown us in the space age, we've got it wrong quite a few times. The space debris problem is only getting worse. We've been doing our best to try and solve it for many years. I talked about Don Kessler and Bert Corpallet's paper almost 50 years ago. The situation has not improved. We're putting more and more objects into space. So we really do need a fix. We really do need a change of mentality. But I think we can do it. I think we can get there. I think it's going to be worse before it gets better, unfortunately. And by worse, I mean, we're going to see collisions in orbit involving probably satellites that are really important and really expensive. And we'll probably go through a phase where we kind of ask, well, how did that happen? How did we let that happen? And what should we do to improve things? And then we'll probably do the same thing again. And I can say that because that's exactly what happened. The last time we had a collision, the Iridium Cosmos collision in 2009. Everybody was kind of wringing their hands saying, how could this happen? An active satellite, no less, getting hit by a piece of debris. Let's do better. And there was a really big push to do better. yet here we are. Debris problem is continuing to grow. So I think it will get worse, and we will see collisions. And I think ultimately, we're going to have to say, enough is enough, and we're going to have to make some hard choices about what we do in orbit. And if we do that, then I think that future starts to open up for us.
You can sort of almost make the analog of how we dispose of rubbish on Earth, and the fact that we've been able to develop such advanced recycling systems now, but you still will have places where rubbish is just dumped and people just litter. And I suppose you would hope that with space, because the means of access to space is so much more difficult to put stuff in space for regular people, that it would be easier to regulate than, I don't know, say fines for someone littering. So maybe that's a bit of optimism. And then I guess I would also hope that the Artemis missions going on, I feel like that's revived a bit of public hope for space. And so maybe that will sort of have a halo effect on all of this as well.
Yeah, I mean, I think Artemis 2, the mission was kind of eye-opening, right? Lots of jaw-dropping imagery of the Earth and the Moon. The thing that really stood out for me is the fact that they have photographs and you can see all the satellites around Earth, right? So for a very long time, one of the criticisms that I've faced and other researchers have faced, when we try and raise awareness of the problem, we use imagery which shows the debris around the planet, and it's really evocative, because rather than seeing this pristine planet in the blackness of space, what we portray is this kind of beehive. It's a cluster of objects that are around Earth, and people always criticise that image, because at that scale, those satellites would have to be the size of Texas, right, in order to show them in that kind of image. Yet the photographs from Artemis 2 show the satellites around the Earth. We've got photographs and video from the International Space Station which show the satellites around the Earth. So what that means, and these are photographs taken from near the Moon. We can see the debris around Earth, and I think for me that's a huge change, right? That all of a sudden, we can't ignore the problem. It is right there facing us from, an orbit that is hundreds of thousands of kilometers away from Earth. We can see the stuff that we've left behind in Earth orbit. That message for me from Artemis 2, I mean, it's probably not the intended message from that mission, but that's the biggest thing that I took away from it. It changes the argument completely. So I think that it is important to embrace all the possibilities that space has to offer, but we have to change our mentality. We are continuing to put more and more objects into space, more satellites. We're using space just much more so now. And all the companies, all the governments are aware of the space debris problem, and they are doing really well at trying to minimise the amount of debris that gets produced. So if you look at each mission that we're doing, they're doing a really, really good job. And that gives me hope. The problem is we're just using space more. And each space mission creates debris. So we're just continually adding more debris. Even though we're doing better at preventing it, the more we use space, the more debris gets produced. So we just have to keep working. So, in many senses, we're on the right trajectory. We just have to keep pushing hard.
Well, that feels like a nice optimistic point to end. So thank you so much for speaking to me. It was really, really interesting.
My pleasure. Yeah, really, really good to talk about this topic, and really good to talk with you about it.